So I have hopefully a quick slide here. There we go. Okay, so I'm going to briefly tell you about my career at Google in one slide. This slide spans 10 years. So yeah, it's kind of sad sometimes. There's actually a little bit before this, but it's probably best not to talk about what that was. Otherwise, I'll just get sad. But I worked on API infrastructure at Google. I've worked on API infrastructure about 8 years now. And when I started working on it, this was the general architecture, right? Google, lots of HTTP traffic comes in. There's a big reverse proxy that sits in front of everything. It routes traffic to a bunch of services. Some of those services implement public RESTful APIs using a library called GData. And I don't know, show of hands, anyone here used AtomPub before JSON was cool? Probably best that you didn't. Okay, so Google was happily building APIs. And when I say happily, not really happily at all. And a couple of things happened, but probably the biggest thing that happened was smartphones. And all of a sudden, a whole bunch of teams at Google needed to build more APIs, lots more APIs, APIs that served a lot more traffic. And there were a whole bunch of API problems that weren't really being solved for people in this GData library model. Now the APIs needed more sophisticated authentication models. They needed quota abuse protection, denial of service protections. They needed terms of service, because if you use the API, you should probably say what you're using it for. And there's just a whole bunch of these cross-cutting concerns that weren't really being dealt with. And so we built up a team to kind of build all that stuff out. And we put all of that functionality into this middle tier proxy, which we called the API proxy, inventively enough. And that's great. And that worked well for several years and scaled up, and we were serving lots and lots of traffic. But there were a couple of problems. So one, there were certain types of services that weren't strictly APIs, right? You didn't pay to call it. You paid for the resources that it used. And so we needed some way to measure that and to track that stuff. And it was the same basic properties that we wanted to track, but they weren't APIs. So we needed a kind of centralized thing that tracked all those behaviors and allowed people to funnel usage data into that and then to emit billing, and enforce quota and things like that. So we created a thing called a control plane. And this is working just fine. And then something else horrible happened, and that's the cloud. At which point, that was way too slow. Right? Having this middle proxy thing in the way, in the middle of all the data paths, talking to the control plane was too slow. Right? There were too many network hops in the way. It was too expensive. We actually built that thing in Java. And it was a single failure domain, essentially, right? There were many different APIs going through that proxy, and that caused spuffs. I myself have taken out significant portions of all of Google API's traffic by pushing config. Config is code, FYI. Don't just push config everywhere. So we needed a different architecture. And we moved on to this model where we created a new version of the API proxy, and we wrote it as a sidecar proxy in C++, and it runs on every job that actually implements the service. The other thing you'll notice is that the protocols started to shift, right? The protocols they start to look more like our internal protocols. Because the truth is that cloud and Google aren't really all that different, right? Everything's on the same physical network. Your workloads run on our machines, just like our workloads run on our machines, and they tend to talk to each other in the same ways. And this was a big trend that was going on. And we had to support orders of magnitude more scale, orders of magnitude reduction in latency, and orders of magnitude reduction in cost to make all this work, right? If you're going to serve an API like Cloud Bigtable, right, which is a very low-level storage API that can absorb millions of writes per second, right, you can't cost the same amount as running a big central managed Java job. It's just not tenable. So that's my Google career for the last 10 years, doing all this stuff. Well, really 9, because I spent the last year doing something slightly different. So, I mentioned a little bit about this kind of cloud and internal convergence, right? So we had the network and the physical distance convergence. I talked a little bit about isolation and reliability. We also had a convergence and security concerns. So when you send us your data, you really want the same kind of protections that we apply to that data when we serve our consumer-facing products. And you need the same kind of end-to-end security and threat protection models that we provide and have been using inside of Google for a long time. And so These are important things. You'll see a lot of cloud vendors obviously building out solutions in this space, but critically important to get this stuff right. So, there's this big convergence going on, and we're using these sidecars for things, but we were really using them for a variety of patterns that were kind of designed to aid integration, right? To help us insert behaviors into the network or data path for services that were massively cross-cutting. And that's a similar problem that most of you have today when you build services, whether they're micro or not. And so how do we take some of the things that we had done and start to apply them to that problem? So as I mentioned before, this API proxy thing is a sidecar, and sidecars have been probably pretty trendy recently. So we'll talk a little bit about how that pattern enables in open source and also vendors to provide solutions that help you kind of start to abstract away some of the concerns at the networking level and also some of the concerns at the security model that you really don't want living in your code. There's been a lot of, I went to a couple of the earlier talks today, and one of the themes in the talks was they talked about decoupling and velocity, right? If you can decouple your operators from your developers, right, they can both do their jobs faster, right? Just like microservices helps you decouple one application concern from another, right, then those two teams building and developing those microservices can iterate faster. You have similar coupling problems at different parts of the stack or different parts of the process. So, this track and a number of other tracks or other conferences, you'll see a fair amount of conversation about decoupling operators from developers. And it's an important trend in the industry because if you have a big portfolio of services, you almost certainly have those two roles. But that's not the only coupling that I want to talk about today. So today when you write services or you write microservices or whatever types of services you want to call them, you very often are writing networking code. Whether it's writing HTTP requests, or you're using a library and you're trying to figure out how to make it work with TLS, or you're trying to configure a load balancer, or anything like that, right? You're either writing code or configuration to configure the behavior of the network, and to make the network do what you want to do. Right? And so one of the things I want to talk about is how do we step back and think about what applications need from the network? I also want to talk a little bit about decoupling the network topology for security. So, traditionally, when you talk to big IT shops and you talk about security, a lot of the conversation will revolve around this notion of network segmentation, right? How do I package workloads into networks with very specific boundaries so that I can precisely reason about what's talking to what and what's not allowed to talk to what? And I think there are some problems with that model because it's not fine-grained enough, it's not portable enough, and it's not flexible enough to meet some of the major use cases we start to see today in kind of microservices development. And I also want to talk a bit about modernization and architecture. You go to a lot of conferences, one of the words you'll hear a lot is lift and shift, right? How do I take my workload and go move it to the cloud? And often you'll see that thread conflated with modernization, right? Do you have to lift and shift to modernize your application stack? I mean, certainly you can use lift and shift to kind of manage your OpEx and CapEx distribution when you're buying compute and storage from a cloud vendor, but is that strongly coupled to modernization? Are there other ways of going about that? And I talk to a lot of people who need to maintain certain IT assets, on private data centers while still also working with the cloud, and how do I make those two things work seamlessly? And all of that feeds into a modernization. Okay, so what is a service mesh? So I like to think of a service mesh as a network for services, not for bytes. Right? Classically, when we deal with networking, right, you reason about sockets, you reason about ports, packets. Maybe you're using an L7 protocol HTTP. I suspect a fair number of you are, but it tends to tail off pretty quickly after you get to the protocol level at L7. And generally speaking, if you're building services, you need a lot more out of your network, right? You'd like the network to route away from failures. You'd like the network to avoid high latency routes to a specific service. You'd like the network to avoid hitting a service that has a cold cache. You'd like the network to tell you when there are unexpected behaviors, latency spikes, packet loss. You also like the network to participate actively in identifying root causes of failure. And you'd like to make sure that the data flowing over the network is secured against kind of trivial network attacks. You'd also like some observability out of the network, right? You'd like to know, well, sorry, let me come back to this a little bit. There's a variety of features that you want, like we talked about observability and security, but you'd like a lot of this given to you for free, right? You'd like to know that, as developers today, right, I don't have to go and buy an awful lot of software to get a variety of properties, right, that I want, right? The long history of software development has been that the underlying infrastructure rises up to meet the needs of the application layer over time. But we've all kind of been sitting at the networking stack at kind of layer 3, layer 4 level for a while, and not getting an awful lot more value out of the network than that. So how do we raise that abstraction up? And when I say free, I don't mean that you didn't pay anything for the software, because that's not really the cost that you probably care about. The cost is that you didn't go and have to rewrite your applications to do it, right? Which would be a much, much more expensive proposition for you. I also care about free as in beer. Istio is actually an open source project, and it is free. But that's the real cost in this system, right? If you have to modernize your applications by rewriting your applications, right, it's either hugely expensive and in many cases completely untenable, right? It's possible that whoever wrote the application left the company 5 years ago. You have no idea where the source code is. No one knows how to build it, but it's still running in production. So that's not that uncommon. So how do you help within that situation? So I talked a little bit about a network for services, but the goal here is to kind of reimagine the network, right? Like you as application developers, what do you want the network to do for you, or a thing that thinks it's the network anyway? Do you care actually which IP and port a packet went to? Like at a fundamental level, do you actually care physically where it went? Do you just care that it went to the right service that did the right thing on your behalf? And knowing that. Right, so if we start to think in those terms, then there's a variety of features I think that we all want. We'd like the network to be able to handle service discovery for us. Right? So when I say I want my sales app to talk to my HR app, I shouldn't have to put into my application code the fact that HR app lives on these 7 IPs at these 16 different ports in these 3 regions and 2 zones and all these different concerns, right? Just don't make me think about that. Please stop. Also, I wouldn't, when the HR app talks to the sales app or some other thing, does it really need to know how to load balance, or should the receiving app tell it, right? Or tell the network how it wants the traffic load balanced? Again, this is stuff that should not live in your application code, right? Because it starts to pile up. And if you think about that for a second, right? We all run in companies or work, with lots and lots of different languages. And networking code is hard. In my history at Google, I worked on a lot of different networking stacks or kind of high-level application stacks, and all the customers of all those things were effectively client libraries writing their own networking stacks that had unique and special modes of failure. And we had some, many interesting examples over the year of applications or clients that caused weird behaviors because they had a quirk in their networking code. And so if you're using some framework to build a set of services, right, that might work fine when both the clients and the services are written in the same language because the framework was designed for that. And maybe the framework is specialized to a couple of platforms and you stay razor focused on that. But as your portfolio of services starts to grow, more languages, more runtimes, more frameworks start to creep in, and then things start to fall apart a little bit. And it can become extraordinarily expensive to keep that consistent. I have a fair amount of experience on that. I worked on gRPC for about 3 years. gRPC's goal is to be a highly consistent RPC framework that spans, a range of languages. That was a huge engineering effort to make sure that they actually all consistently behave the same. And the truth is they don't, right? They have little quirks that occasionally make things go funny. So how do we solve that problem? And particularly solve that problem when you're dealing with application code that can't be updated, right? You can't go put the shiny new framework into it, right? You don't really control it. So how do we go about doing this? I'm sorry to do this all to you right after lunch, but this is going to be a heavy meal. But we use sidecars. And what Istio does is it injects sidecars into both sides of the network. And doing that allows us to do a number of things. If you look at the set of outbound features, right, so service A wants to talk to service B. When service A starts to make a call, Istio transparently captures all the network traffic, routes it through the sidecar, and the sidecar layers in behavior that you want. So the sidecar on the client side can inject authentication credentials, it can load balance calls the other side, it can inject failures if you want to do chaos stuff. If you need fine-grained routing control, it can have received a configuration to split traffic off to go somewhere else. It can do tracing for you, so it can start and initiate tracing. And there's a variety of other features that I haven't listed on here, but it gives you a lot of power in the network, right? Because now you have a smart endpoint that belongs in the same trust domain as your application, right? It's really logically part of your application. And we'll talk a little bit about the security properties of that. That is able to take on a whole bunch of application level concerns for networking. So you can kind of consider it like an out-of-process library in some ways, right? Like whichever mental model works for you. But the truth is that it's part of the application, but it's just not in the process space of the application. Similarly, on the server side, right, the server sidecar is in the trust domain of the receiving application, so it's totally fine for it to do authentication on that side. It can check that it's received a credential that's appropriate for the call. It can do authorization, right, checks. So if you have a centralized ACL management system, then it can enforce policies on that. It can implement rate limits, right? A lot of production systems or medium-sized production deployments don't often do rate limiting. But as you grow in scale, right, one of the more common forms of DOS attacks is the internal data accidental DOS attack, right, where somebody runs a load test to test the service and it has an unintended consequence and takes out the system. Right? Accidental DOS or drive-by DOS or whatever you want to call it. Also, load shedding is a big part of that, right? If I can prioritize which requests I want to drop on the floor if I'm in one of these modes, right? If I'm in a DOS mode. And again, it can participate in request tracing, it can provide telemetry, which we'll talk a little bit about, and it can inject faults to trigger behaviors and see if your system is behaving or recovering as you would like it to. So that's kind of Istio in a nutshell, right? That's the fundamental architecture. So how do we put it all together? Well, we have, as I showed you here, the sidecars, and there's a control plane that sits on top of that configures the behavior of the system. Right, so there's an API that sits above that basically operators or developers or whomever actually wants to affect these types of things pushes configuration in that says this is the behavior I want the network to have. And then we have a component on the left called pilot, and its job is to distribute that configuration, that intent, down into all the sidecars so that they implement those behaviors. So mostly that's just pushing configuration down into Envoy Live. Envoy is a really interesting proxy because it is to receive an update of its configuration. It does not need to restart. Right? This is actually a fairly novel thing in networking and proxy land. So it's an entirely API-driven configuration model for the proxy, and it stays up the whole time. So you want to change a networking route, has no impact on like hopping, on SLO, on availability. Right? It just changes its behavior. We have another component on the right-hand side, which is called Istio-Auth, and its job is to inject certificates down into the sidecar and to rotate those certificates on a pretty regular basis. And the reason why we send certificates down into the sidecars is because we actually use that to identify the workloads and to secure the traffic between both sides. And I'll get into some more details about security later. And then the last part, the piece in the middle, which we call the mixer, is it's the extension model of Istio, effectively. It receives telemetry from the sidecar proxies, which then federates downstream to whichever telemetry collection system you want to work with. But it also implements a policy check. Right? So the server-side sidecar, when it receives a call from the client, will call out to Mixer and say, hey, should this call be allowed to go through? And the information that's available to make that policy decision is dependent on the protocol that's being used. If the protocol was HTTP or gRPC, right? We can send a lot of information to Mixer at kind of layer 7 information about the call to enable Mixer to make that type of policy decision. And obviously, as I mentioned down the bottom corner, we try to do this as transparently as possible. So in the case of Kubernetes, we do a little magic in Kubernetes land, which effectively kind of rewrites your pods on the fly to inject this networking behavior, and you don't have to know that it happened. And segregating operator roles so that operators can basically enforce that this happens for all the workloads deployed into a Kubernetes environment. But it's not. This model is not tied to Kubernetes. We just did a release of Istio that showed you how to do this with VMs. We're working with Mesos to make it work in that environment. We talk to Docker folks a lot. Right? This pattern just generally applies. We actually don't care too much what orchestrator you use. It's the same basic model, right? So I mentioned a little bit about Envoy. I saw the DataWire guy earlier talk about Envoy, and he's got good taste. So it's a C++ proxy. I've worked on proxies in a variety of different languages. The first 2 iterations of the stuff I worked on Google probably should have been done in C++. It's just, there's really solid tooling behind it. You can get a lot of performance. You can get a lot of really interesting and quirky things that are just super hard to do in other languages. And it's been used at Lyft for quite a while. They have beaten it to death. And it scales up pretty well with their service. They've been very happy with it. And they've also been a great community to work with. If you ever get a chance to go see a talk by Matt Klein, I recommend it. He's one of my favorite angry men in tech. And his Twitter feed is pretty good too. But I mentioned the API-driven updates. It also has features like zone-aware load balancing. It does HTTP2 both on the inbound and outbound side, which is actually pretty unique in the industry today. But probably more important than that, it was designed for observability, right? Envoy and Matt, they had this philosophy of making behavior of the network a first-class thing, and if you can't really do that unless you know what it's doing, right? So Envoy actually produces a lot of information about its internal behavior that's easy to scrape and feed into downstream telemetry systems, and that has really helped them with their production rollouts, with understanding how systems are behaving, when they're having failure modes, being able to diagnose it. So how do we model this? So I talked a little bit about Kubernetes, but we're effectively environment agnostic. But we need to understand the topology of the network. And really that means we need to understand either service discovery tools or orchestration tools, because they effectively dictate the topology of the network. So we have this system called Pilot, which is the thing that programs envoys, and it receives basically topology information from Kubernetes or from Console or from Eureka or from whatever you want to write and plug into Pilot. Right? So we suck in all this topology information, and then we merge it with the configuration that you apply, this rules API that dictates the shape of the traffic, to create this abstraction over the network topology that we then emit down into the stack. So we've done a number of integrations. I mentioned Console, Eureka. There are other ones going on in the Istio community right now. And so, if there's one that isn't being tracked there that, you'd really like to see covered, come and let me know afterwards, or go file a GitHub issue. That would be great. And then, as I mentioned before, we push the configuration down into the network, and we don't hot restart Envoy to do it. Or at least we try very hard not to. And if it is hot restarting, it's a bug. It's not a feature. And that's how we program the network. So let's get back to some of the other kind of high-level features. I talked a bit about observability and the kind of the properties of Envoy. What do I mean by observability? Right. So you have this, this mesh of applications that are all talking to each other. These services. They probably all have names. They probably all run under a certain authority. They're probably all performing different sets of named operations or roughly named operations on resources within your kind of application domain. They may live in different zones. They may have different physical characteristics. They have, when you make a call, it has latency, error distributions. All of that is a set of information that you want to be able to easily extract from the system and be able to put into nice shiny dashboards, into analytics pipelines, perhaps into things that actually feed back into your deployment management and CI/CD systems, so you can reason about incremental rollouts. So that's what we mean by observability, right? We mean to be able to extract as much information from the network as we can and package it up in a way that's easy for you to consume. And that's what we want to do in Istio, because we can actually see a lot of what's going on and help operators fill in the gaps when the application isn't really helping them fill in the gaps. Right? A good example here would be, want to show a graph showing all the different operations invoked by a service and the latencies or the 90th percentile latency for each of the operations. But the API is RESTful. Right? It's hard to actually generate graphs of RESTful operations unless you actually classify the operations. Right? Paths are, if they're highly parameterized, they make a terrible classification system. So maybe you want to use something like OpenAPI to classify paths into operation IDs and then generate your graph that way. But you don't want to rewrite the application code, so how would you go and do that? And we'll provide some means by extending Mixer to be able to classify traffic so that you can feed that back into the telemetry system, again, without updating the application. So today, Istio ships with a kind of out-of-the-box monitoring experience. We use Prometheus and Grafana to do that. And you get these metrics without instrumenting your apps. We show you metrics that are keyed by both the source and the destination of the traffic. Right? So I can have a graph that says how much traffic is going between service A and service B. Right? Not just how much traffic is going into service B. Right? That's a very powerful tool. I can also trace requests. Now, obviously, tracing requires some participation on behalf of the application layer to propagate context through the application code itself. But Istio can help you with initiation, sampling, etc. It can make the behavior of the network as it kind of flows around the application parts visible to you. Right? So you can see network latencies as well as internal application latencies if you've properly instrumented your code. And we want to do this in a kind of vendor-neutral way. So actually, there's an extensible pipeline that goes out the back of Mixer that plugs into a variety of different instrumentation systems. We use Zipkin today in our kind of out-of-the-box experience, but I expect we'll probably ship other out-of-the-box experiences, or you'll see other vendors ship different types of out-of-the-box variations. There's certainly plenty of choice on the monitoring side. Maybe you like, I don't know, commercial vendor like New Relic or Datadog or Splunk. On the tracing side, maybe you want to use Lightstep or Open Tracing or whatever you want to use. We actually don't care. Right? We just want to make sure that it's easy to integrate that and extract that information from the network and push it down into these tools in coherent ways. So basically, this is an example of the topology. Showing you Prometheus here, which is the one that we ship, but we've also done examples with StatsD and obviously Google Stackdriver. I do work for Google. There will be occasional plugs. And then we have GUIs. We show you. I kind of showed you the Grafana one on the previous screen. Actually, Weaveworks, which is a company based in London, they have a kind of observability demo that they do using their tool, sitting it on top of the Istio metrics, and then showing you a whole bunch of interesting stuff. So, if you want an actual product that does those types of things, they're good people to talk to. And it's done that thing again. Okay, so let's talk about resiliency for a second. I think there's some talks today about chaos engineering. This is something that Netflix kind of pioneered in the ecosystem for many years. What are the features that you want out of the network that help you make sure your application code is well behaved in the face of failure? People talk about timeouts. Timeouts are a very useful tool. They're also kind of a double-edged sword if you're not careful, but they are an important tool in the kind of operational toolbox to make sure that your system stays stable. Maybe you want to try a read from a remote service. If that read fails in a certain unit of time, I can read out of a cache or some more stale data structure and still serve content to the user with a reasonably high SLO. So timeouts help you do things like that. Retries, retries are the sharp end of the timeout world. If you have cascading retry problems causing outages, it's another great example of accidental DOS attacks. But there's a variety of other things: circuit breakers, health checking. Maybe you want to be, availability zone aware because your application is big enough to span multiple geographic regions, and you want to make sure the system actually routes traffic appropriately when bad things happen in zones and things like that. And you also want to do things like systemic fault injection, right? At Google, we run a kind of annual exercise called DIRT, where we make certain key systems start to fail, like periodically, intermittently, or in very specific tuned ways to elicit awful behaviors in their dependencies. And this is something that I think the community should probably, it's a thing that people should definitely be doing as part of their operational management approach to rolling out big, complex applications into production. Anyway, on the left-hand side, you can see an example of a configuration object which you send to the Istio control plane API, and basically says, here's a bunch of properties about how I want the network to behave in this situation. And the situation in this case is any traffic going into that destination service. And we have a fairly sophisticated language that allows you to kind of apply these controls to intersections of both source and destination. Traffic control. Okay, so that's the resiliency side of things, but there's lots of use cases. They don't really have too much to do with resiliency. You might be more looking to do blue-green deployments, or I might have to solve the virtual hosting problem, or a variety of other types of things where I just need to make sure the right traffic goes to the right place. So here's an example of traffic splitting. Traffic splitting is important because you want traffic splitting to work at the right layer in the networking stack. If you look at Kubernetes today, Kubernetes has this kind of load balancing system for pods, which is layer 4 based, which means if one pod wants to talk to another pod, then the traffic is load balanced at layer 4, not at layer 7. So if you want to roll out a rule that says I want 1% of HTTP requests to go to that other pod, you can't do it. You need something that gives you that kind of flexibility. And this is a common practice in the industry, right? Traditionally, mostly done using middle proxies. And now we're just pushing that same set of functionality down into the sidecar on the client, so it just happens from the client at origination. And here we're just showing you basically a weighted percentage traffic split between two destinations. Similarly, you might want to do what we call traffic steering, which is not just dividing traffic up arbitrarily based on percentages, but actually dividing traffic up based on some property of the traffic. The example we show here is a user agent filter. I want to send iPhone traffic to one service. I'm going to send Android traffic to some other service. This is a fairly simplistic example. The routing rule can actually be quite complicated. I could actually write a rule that matches based on the source here as well. So I can do some pretty complex combinations of these things to test out, variations of traffic and behavior that allow me to influence rollouts or a whole bunch of properties in my operations side of things. Okay, so I'm going to give you a heavy meal about security for a second because it's an important point. When it comes to securing services, what are the things that you actually want to do? Right? We talked a little bit about segmentation, right? So you want to make sure that only the services that are supposed to talk to each other are talking to each other, and only the operations that they're allowed to use when they talk to each other are talking to each other. Well, there's a couple of things you need to do before you do that, right? One, you need to make sure that you know who the service is, right? Who's calling you? There's no point having a policy if you can't, in a strong and verifiable way, know who's calling you. Because otherwise you might as well be guessing. So we have this notion of verifiable identity. You want to make sure encryption is on by default. So one of the things that we do at Google is we assume that our internal production network is insecure, that there could have been a penetration attack done to any workload running on any node in the network. And how do we protect all the other things running on the network from that event? Right? I'm not saying that that's happening. I'm just saying that that's the mental model, right? We want to have defense in depth against a whole variety of different types of attacks. One of those obviously attacks is sniffing the network, right? So you want to make sure that payloads as they go between services are encrypted, and that encryption is verifiably tied to the identity. We have another kind of reverse problem here, which is the kind of secure naming problem, When service A wants to call service B and it gets an IP address back, how does it really know that that IP address is part of service B, right? So that's what we call the secure naming or addressing problem. And then we want to be able to respond to threats rapidly. Right? So what Istio does is it issues certificates to all the workloads that allows them to identify each other and use mutual TLS to provide verifiable identity and encryption by default. So that's how we know who's talking to who. But if service B is being compromised, I want A to stop talking to it as fast as possible. So what we want to do is revoke B's credential. So we have tools to support rapid revocation so that that connection from A to B will terminate either within a limited time window, right? So we can limit the blast radius of a particular security event to time, right? Which is a very important property of your security posture. We can often do better than that, right? We can shrink it down into very, very short amounts of time. And why is this important? So if you think about strong service security at scale, what are the concerns that you might have? Well, you should be concerned about insiders, right? Either accidental or deliberate, right? One of the biggest potential security risks to any company is the people who work at the company or people who accidentally walk in the door and stick a USB thumb drive into a machine. You have to worry about hijacked services, right? And this is a problem with perimeter security today. Like, Equifax is probably the gold standard nowadays of hijacked services, unfortunately. And what hijacking means is that whatever was hijacked, which it now becomes a malicious agent, gets to use all the properties and power that the service had before it was hijacked, right? So it's part of its trust domain. And so if everything around it trusts it implicitly, either because it's network reachable or for some other reason, that's not good, right? Trust needs to be managed in a fine-grained way. But fine-grained models are hard to manage, or at least fine-grained networking models are hard to manage, right? If you want to push out tens of thousands of firewall rules, how do you reason about fine-grained security? Like, what is the mental model you want to have? When I talked, as I've been talking, I consistently say the word service A wants to talk to service B. Right? That is the natural mental model, I think, in the microservices world. So how do I say this is service A and this is service B? And how do I do that when service A is very mobile? Right? If I'm using something like container orchestration, service A isn't going to just sit there on one IP and one port for the rest of its life. It's going to move around a lot, possibly quite quickly, in many geographic regions, and it might even move onto your development laptop. Right? We talked about test in prod. Well, that's also there are variations of that which are develop on your laptop and have your laptop, the thing you run on your laptop, which is one of the services, be able to call some of the other production services which are running in the cloud. All right, now your network perimeter model has to be way more flexible to accommodate these types of things. You also want to be able to reason about securing resources. I mentioned securing APIs and operations within APIs, but resources are kind of the next level down in granularity. All right, I have a database. That database is a resource. I have a file in a file system. Right? I may have one API to read and write files, but one of those files is way more valuable than the other one. Right? So I have to be able to reason about those types of things. And at some point in your life, you might have to deal with audit and compliance, either for statutory reasons or because it's good practice. Right? I'd like to be able to know what my security posture is, and are there things I can do to make it better? And then there's a whole bunch of wants that you have, right? I mean, I mentioned workload mobility. It's both a concern but also a want, right? You might want to be able to move from one cloud provider to another, or run some workload on-premise and some workload on cloud, and be able to move back and forth between those two things based on whether it's cheaper or easier or more performant or whatever your criteria are. I want to be able to administer this remotely, do local development, right? Bring your own device is a really common theme, not just in the developer community, but also in the enterprise world in general. I'd also be able to reason about people and machines in a somewhat similar way, right? When I talk about authority, I talked a lot about service-to-service authority, but a lot of what happens in operations land is user-to-service authority, All right, and how do I reason about those two things in a consistent way? Right, if they're entirely distinct, it makes it very hard to think about like what the security properties of my system are. And I want to keep costs down. Right? A lot of this, if you want all these properties and you want to deal with all these concerns, right, you could be looking at a pretty hefty bill. So, Google's approach effectively is, we don't believe that traditional perimeter security models are sufficient. We think they're useful, and we certainly do a fair amount with network perimeter, but we have an additional layer on top, which is identity-based, right? And strong identities, verifiable identities. So here's a kind of quick overview. I showed you a little bit of this before, but we have a CA. It provides certificates. They're pushed down into the sidecars. Those certificates are rotated. Those certificates have an expiration that's usually quite short. And then Envoy initiates mutual TLS between the two sidecars. And that's how we get verifiable identity in crypto. And then those identities are passed up into the policy layer to make decisions. So I might just kind of glide over the policy stuff really quickly. So we showed you this earlier. But the policy stuff is, Mixer is the component which enables kind of integrating extensions into the system. So in the Istio community, we've done work on, say, open policy agent, which is an emergent spec to allow people to declare policy constraints on network or system or service behavior in a kind of standardized expression language. So we have an integration with that. We provide whitelists and blacklists as features out of the box. We'll probably do integrations with LDAP systems. Heck, we might even do an integration with Kerberos or Active Directory. But the goal really is to kind of funnel all those things through a common API, and an API that enables us to cache policy decisions as close to the edge as possible, so that if those downstream policy systems start to fail, the network stays up. That's the goal. It's not an easy thing to do engineering-wise, so we're still kind of working through many bumps with that, but that's the goal. And that's as opposed to saying every one of those policy systems is individually integrated into the edge. Right? And the problem with doing that is then you start to see inconsistent failure modes between those policy systems, and it's hard to maintain the aggregate SLA. So there's a reason why we funnel everything through one standard integration point with a common API. It's mostly so we can dictate caching behavior for system stability. And this stuff is focused at operators, right? So we want to say, hey, operator, what are the properties of your network that you want? Integrate them. And then here's a configuration model so you can manage and roll them out without requiring application developers to go and create a new build so you can do that. Okay. So here's some examples of some attributes that we produce, and we call this the behavioral vocabulary. And it's a very long list of things. If you go to the site, you can see more of this stuff. Here's a short roadmap, and I think this is probably a good point to switch over to questions.
Quick question. I think I saw it in the roadmap. I just want to verify. Are you going to plan to do stuff cross-cluster, so like two cluster and mesh between them? Okay.
So when I talk about workload mobility, right? Obviously, Istio has to be able to deal with workloads that span many physical locations, different orchestrators, on-prem, cloud, you name it.
And how far are you from that?
Ask me after Christmas.
Okay.
Hi, I have two-part questions. So you moved a library into a process by itself in a sidecar. Why not take it one level further and move the sidecar out in a cluster, which is a traditional reverse proxy cluster? And the second part, the rationale behind that, we do that way is because the only problem we have is deployment lifecycle of the proxy, like in Envoy. For example, we have a new build for a sidecar to push. We are dependent on the app to update itself, and
it's a good question.
To decouple.
So one of the reasons why we run Sidecar is because we want it to be part of the application trust domain, right? When we issue a certificate, that certificate identifies the application. If we try to do the same thing with middle proxies, now middle proxies are superpowers, right? They're able to act on behalf of n other things in the network. As soon as you exploit the proxy, you have a big blast radius problem, right? So you want to scope down the privilege of the credential, but also the workload with which that credential is associated. Now, we do plan to do a variety of things to help people manage the update of sidecars. While Envoy, we try not to hot restart it, it does have a lot of hot restart capability to migrate traffic in place. And so we think we can probably do binary rollouts in cooperation with orchestrators without actually impacting traffic at the sidecar level, but it will require some qualification to make that work. But that is the goal. I'm not also saying that middle proxies have no role here. Right? We actually, in Istio, have many use cases for middle proxies, but we try and not turn them into superpowers. It's very important.
Hi, related to the proxy discussion and what you have on your roadmap in terms of API management, can you talk a bit more about what you expect to happen on the API management side and how that plays with the proxies?
Sure. So I kind of gave a subtle example of one thing that API management does today, and that's classify API features, right? If you can classify features of your API, extract IDs out of RESTful endpoints, maybe using something like OpenAPI, then you can start to tie features like quotas, ACLs, those types of things to those features. Now, I mostly talked about this for the the internal to internal use case. But those same set of behaviors are equally applicable to the external to internal use case, right? Which is classic API management, right? If you go and look at what those vendors sell. There's a variety of other features, in the kind of the long tail of API management, right? So content transformation, end user identity integration, things like that, which we do intend to provide support for at the platform level. So for instance, you'll see signed JOT support come out in Istio in the not too distant future. There's a variety of things in there.
I had a question about any transformations on the incoming payloads. So you showed the example of how you can key on a header value or something like that for routing. Is there extensibility to that? For example, if I wanted to integrate with a MaxMind geolocation database, could I make those kinds of extensions?
Oh yeah. So I mean, Mixer is designed to be an extensible platform. Right, so we have a documented plugin model. We have a guide telling people how to write extensions for it. Right, so that's the primary extensibility model. There will also be a kind of API-based extensibility model, where all that, all those signals that we're extracting from the network, there will be a standard API that you can implement that will receive those signals and also provide feedback to Envoy to both augment traffic and control routing behavior.
Great. So let's thank Louis one more time.